So the next ones, we're going to build on those compound angles to create what we call double angle formulas. So sine of 2 theta. Well, I can rewrite 2 theta as theta plus theta and then use our sine cos cos sine. So it'll be sine theta cos theta plus cos theta sine theta. But of course they're the same thing. So we end up with the first of our double angle formulas, sine 2 theta, 2 sine theta cos theta. So if you ever do forget it, remember where it comes from. You can always go back to the compound angle formula and create it if you need to. Cos 2 theta then, cos theta plus theta. So cos cos minus sine sine. But cos cos is cos squared, and sine sine is of course sine squared. We can actually write this another way, because I could, instead of writing sine squared, write that as 1 minus cos squared. And then I get a formula all in terms of cos. And so we get 2 cos squared theta minus 1. Or I could write it all in terms of sine. So change the cos squared to 1 minus sine squared, and we get 1 minus 2 sine squared theta. So it's cos squared theta minus sine squared theta. But if we want it in terms of cos, notice we then get 2 cos squared minus 1. So the cos squared is positive. Whereas if we want it in terms of sine, we get 1 minus 2 sine squared. The sine squared is negative. How do we remember that? We go back to the original formula, cos squared minus sine squared. So the cos squared is positive, the sine squared is negative. And tan, we get tan plus tan on 1 minus tan tan, and then that tidies up to be 2 tan theta on 1 minus tan squared theta. So we call them double angle results, not 2 theta results. Because you could use this to find the sine of 4 theta. Because 4 theta is double 2 theta. So you're saying it's double the angle. All right, let's summarize those in a box, because that's just a fun thing to do. All right, sine 2 theta, 2 sine theta cos theta, cos 2 theta, cos squared minus sine squared, or it could be 2 cos squared minus 1. Now, this will become really useful later on when we're doing integration. And I'll remind you about this, and you'll go, what? I don't remember that. And then, thank goodness I remind you. Because when we want to integrate cos squared, we can rewrite this formula to be a half of 1 plus cos 2 theta. So that little relationship will end up becoming very, very handy indeed. And there's a similar one, the 1 minus 2 sine squared, I could rewrite to be sine squared as a half of 1 minus cos 2 theta. Yeah, they're very similar, but notice the cos squared has the plus, the sine squared has the minus. So again, it matches with that cos squared minus sine squared. Tan 2 theta, 2 tan theta on 1 minus tan squared theta. All right, let's do some examples. If cos theta is 2/3, find the tan of 2 theta. All right, I'll draw myself up a little triangle. Cos theta is 2/3. The other side then is root 5. Tan 2 theta, 2 tan theta on 1 minus tan squared. Sub in. And eventually, there we go. That one all tidies up to be minus 4 root 5. Find the exact value of sine 5 pi and 12 cos 5 pi and 12. Well, our double angle result is 2 sine theta cos theta. So I've actually got half of that. But then I know, okay, this is a double angle result, so I can rewrite it as sine double the angle. So it becomes sine of 10 pi on 12, which is, of course, 5 pi on 6. And a half of that, sine 5 pi on 6. 5 pi on 6, second quadrant, isn't it? So sine is positive, the acute angle is pi on 6, which is the same as 30. Sine of 30 is a half. So we get a half of a half, a quarter. If cos theta is 2/3, find the exact value of sine half of theta. So theta would be double a half theta. So I can still use the double angle result here. I'm going to use that rearrangement of the cos 2 theta formula. So I'm going to go sine squared is a half of 1 minus cos 2 theta, because I want to find the sine of the single angle. So I'll put it in terms of the double angle. So that's going to be the same as saying, just to highlight it, if I rearrange that, sine squared of theta on 2 then would be a half of 1 minus cos theta. They've told me cos theta is 2/3. So I get that sine squared is 1 on 6. Well, best I can do at this stage is plus or minus 1 on root 6. Because they've told me cos theta is 2/3. Well, if cos theta is positive, I could be in the first quadrant. And when I halve that, I'll still be in the first quadrant. But sine's positive, so that's okay. But I might be in the fourth quadrant. Now, if I double the fourth quadrant, halve the fourth quadrant, I should end up in the second quadrant. Well, hang on, that's still positive, isn't it? But then I could go around again, so I might be 360 plus theta, and when I halve that, I think I end up in the third quadrant, somewhere in there. So it is possible it could be negative. Without more information, I guess is what I'm getting at, is we don't know. Is it going to be plus 1 on root 6, or is it going to be minus 1 on root 6? Prove this trig identity. Square root of 1 minus cos 2x is on 1 plus cos 2x is the same as tan x. Okay. Well, I'm going to use my cos double angle results. But looking at my answer is tan x. Remember, tan is sine on cos. So for the top double angle result, I'm going to use the one in terms of sine squared. For the bottom one, I'll use the cos squared. So I'll get 1 minus 2 sine squared on top, 1 plus 2 cos squared minus 1 on the bottom. That leaves me with 2 sine squared on 2 cos squared. The 2's cancel. Sine squared on cos squared, which is tan squared, and the square root of tan squared is tan. Here's one from an HSC. Prove that this is equal to 2. Some people wasted a lot of time with this particular one because they saw the sine 3 theta and they thought, hang on, I've got to use my compound angle results to work out what sine 3 theta is. But if you put it all together as an algebraic fraction first, something nice happens. Look at the top of the fraction. Sine cos, cos sine. So actually I could rewrite the top one as sine 3 theta minus theta. Well, what I've then done is multiply top and bottom by 2. So on the bottom I now get 2 sine theta cos theta. So on the top of the fraction I have 2 sine 2 theta. On the bottom of the fraction I just have sine 2 theta, and that gives me 2. That's it. If you had worked out a result for sine 3 theta and cos 3 theta, it would still work. This is going to take you a lot more time, of course. Here's one from 1994. My goodness. 2 tan A on 1 plus tan squared. Oh, very tempting to look at that and you see the 2 tan on 1 plus tan squared and you think, oh, there's your double angle. But no, it's not. The double angle was 2 tan A on 1 minus tan squared. So this is 2 tan A on 1 plus tan squared. All right, I've got to turn this into sine 2A. What shall I do? I guess I'll just change all my tans into sines on coses and go from there, because I want to end up with sine 2A. So I want sines and coses. So I get 2 sine A on cos A, 1 plus sine squared on cos squared. Fraction on fraction. What about we multiply everything by cos squared? So on the top we get 2 sine A cos A, and on the bottom, cos squared plus sine squared. I think we got it. Because of course, cos squared plus sine squared is 1, and then on the top of the fraction, there's our 2 sine cos, so that's sine 2A, which is what we were trying to prove. Number 6 there. Sine of 2 times the inverse cos of 3/5. Remember, inverse cos, we talk about an angle there. Let's say that angle is theta. And then all we've got there is really sine 2 theta. Let's draw up a triangle so we can work out the other ratios. So theta, cos theta 3/5, the other side's 4. So we're saying sine 2 theta, which is 2 sine theta cos theta, read off the triangle, and we get 24 and 25. the inverse cos of 2 cos pi on 3. Well, in this one, cos pi on 3 is one of our exact ratios. So cos of 60, isn't it? So cos of 60 is a half. 2 times a half is 1. So we're just saying, what's the inverse cos of 1? 0. Okay. So 17e we shall look at